In this video, we're going to do electron configurations and energy level diagrams for ions. So some great background information you'll need to know for this particular lesson is what an ion is. And remember, an ion is just an atom with a charge. That's all it is. So they're charged atoms. And the only way to become charged, the way to become a charged atom is to either lose or gain electrons. So there's two main types of ions. There are cations and there are anions. The cations are positively charged. The anions are negatively charged. And you can remember that trick with the T over here. Looks like a plus when you write it out, cation. Or if you like cats, you can think they're positive and cute. And then for anion, if you write it out, you could say a negative ion. Or you could say it looks like onions and you don't like onions. Unless you do, then ignore that trick. So cations are positive because they have more protons than electrons. And that's because they lost electrons. So to become a cation, you lose electrons, one or more electrons. And to become an anion, which is negative, you have to have more electrons than protons. And that's because you gain electrons. So for example, if we look at our periodic table here, you can see that different elements tend to do different things. Some will gain electrons, some will lose electrons. So if we look at sodium, when it forms an ion, will lose electrons. So when it's forming the ion, we're going to have Na plus 1 plus an electron. That means that sodium, this is sodium metal, just the neutral atom, and then it became sodium plus 1 by losing 1 electron. So that's released now. Whereas something like, let's say, calcium would become, you can see it wants to become a charge of 2 plus. So that means that it lost 2 electrons. Some elements will gain electrons instead. So if we look at oxygen here, oxygen will gain 2 electrons and will become the oxide anion with a charge of -2. And so it became an anion. Whereas, let's say, fluorine, on the other hand, you'll notice it wants to become a charge of -1. So it gains 1 electron to become fluorine with a -1 charge, and that's fluoride. And you might remember that from grade 11 and grade 10, that typically non-metals will gain electrons to become like the noble gases that come after them. So fluorine will become like neon. Chlorine will become like argon. Same thing with sulfur, like argon. Same thing with oxygen, like neon. Whereas the non-metals, the metals, they tend to lose electrons to become like the noble gas before them. So lithium loses to become like helium, and beryllium loses to become like helium as well. Sodium loses to become like neon. Magnesium loses to become like neon as well. And this is all related to their ionization energies, to their electronegativity values as well. But this is a simplified way to just review the concept of ions and anions. Of cations and anions. So again, when anions form, it's because they're gaining electrons to become like the noble gas that comes right after them. So they want to become more stable. They want to have a full valence shell. And we can represent that in our electron configurations, just like you used to do with Bohr-Rutherford diagrams or Lewis structures. So for example, let's say I want to show the sulfide ion, which is the ion of sulfur. So generally, you would draw a Lewis structure and say sulfur has 6 valence electrons because it's in group 16. And you would say, well, it wants to gain 2 electrons. So you would put 2 electrons there so that it could fill its valence shell. And you'd put -2 in the brackets. So that was a Lewis structure you would do in grade 11. Now in grade 12, we need to do the same thing, but instead we're going to do it with energy level diagrams and electron configurations. So if you're told to draw the anion, what I would do is I would start off by drawing just the regular neutral atom. So sulfur, if we look in our periodic table over here, is number 16. So it has 16 electrons. And so that means we have to place 16 electrons in our energy level diagram. So let's go ahead and do that following all our principles and rules. So here we go. That's so far 4. Place them singly first, then pair them up. That's so far 10. And then we have 11, 12, 13, 14, 15, and 16. So this is the neutral sulfur. And if you didn't know what ion sulfur formed, you would look at its highest energy levels. And so the highest energy level, we have 3s and 3p. Those are typically the valence electrons, the ones in the higher energy level. So we have 3s and 3p. And you would see that when you're forming an ion, what you're going to do is you're going to add extra electrons so that you can fill up the highest shell that remains. And that's the case for nonmetals. So add extra electrons to the total number of electrons in the atom before proceeding to distribute electrons into orbitals. And so we're going to add our extra electrons to fill up the 3p orbital over here, or 3p orbitals, I should say. Here they are, so 1 and 2. And so to fill up that last sublevel, we added 2 electrons, the red arrows there, and this would be our sulfur 2-. And what you might notice is this actually looks very similar to, looks like argon. So sulfur gained 2 electrons and now has essentially the same electron configuration as argon. We would actually say that they are isoelectronic to each other. So S-2 and argon are isoelectronic. Iso means the same. So that just means that they have the same electron configuration now. They're not the same element because they have different number of protons, which is why sulfur is charged and argon is not, but they have the same electron configuration. Let's take a look how to do this for the complete electron configuration of the sulfide ion. So what we're going to do is we're going to write out the electron configuration for just regular sulfur first. So I'll do sulfur over here. And I'll use my periodic table technique. So sulfur has 1s2, 2s2, 2p6, and then 3s2. So 1s2, 2s2, 2p6, 3s2. And we're almost done. We have to make our way to sulfur here. So now we're in the 3p's area. 3p1, 2, 3, 4. So 3p4. And so what you'll notice is that we don't want to take away electrons. We want to add electrons. We're going to add electrons to the highest energy level that we have available here. And it's really the only thing we can add electrons to because this is the only one that's not full yet. And so the P can hold a maximum of 6. So that's what we're going to do. We're going to add 2 electrons to our P sublevel there in the highest energy level to get the ion. So 1s2, 2s2, 2p6, 3s2, 3p6. So we added 2 electrons, and that gives us our S-2. And you'll notice that this is essentially the same electron configuration as argon, because now we have the same number of electrons. It hasn't become argon because, again, we have different number of protons, but same electron configuration is now there. And for shorthand, so let's say for sulfur, let's do the same color so we don't get confused. So for sulfur shorthand, I want to go to the previous noble gas for sulfur, which was neon. So neon ends at 2p6. So I'm just going to underline this here. That's where neon ends. So now I'm just going to replace this with 3s2, 3p4. And then for sulfur, on the other hand, or sulfide, you'll notice it's just argon. So it's simply Ar. And that is our electron configuration for the sulfide ion. So when you have a nonmetal, you want to add electrons to its final sublevel to fill that up. Essentially, you're completing the valence shell of that nonmetal. And it becomes like the noble gas that comes right after it. So that proceeds it, that comes right after it. Okay, so bromine would become like krypton, for example. Iodine would become like xenon. You're adding to that valence shell. Now, just to clarify, when we're looking at valence shells, generally in this area here of the periodic table, the valence shell is going to be your highest S and P level. So here it's your 2S, 2P. Here it's your 3S, 3P, 4S, 4P, 5S, 5P, 6S, 6P. So those are your highest energy levels, and those are your valence electrons for the most part. So like we saw in the sulfur example, we had our valence electrons were the 3s and 3p, and we could fill up the 3p because it was a lot easier to just fill up 3p than to empty the 3p and empty the 3s to get a full shell below. So let's go and take a look at how to make cations now. For cations, you're generally going to see that happen when you have metals for the most part. And what you're doing is you're removing the outermost electrons so that you can have a full shell somewhere. So for cations, draw the full set of electrons of the neutral atom first, then remove the required electrons from the highest energy level. So typically what you would do is when we say highest energy level, this is the order you'd kind of see. So the outermost, it depends what you have, it varies, but generally you want to remove the outermost electrons. So first you'd want to remove from P if you have an outermost P shell. If you don't have an outermost P shell, or you do, but you've removed all the electrons there, you might want to remove from S. And then if you've removed all your S, you could also sometimes remove from the D. So you might remember that there are some elements that can have more than one ion. That's because their valence electrons are actually can also be from the D orbitals. They can also sometimes be S and P orbitals that give more than one charge, but many times there are those transition elements in the D block that actually have valence electrons that are considered D. You have access to those as well due to energy. So we're going to try an example together. We're going to draw the zinc ion energy level diagram, the electron configuration, and the shorthand. So zinc is in our periodic table. So we're drawing zinc. First, we'll start off by drawing zinc, and then afterwards we'll make its ion. If we look at zinc, let's go find it up here. Zinc has 30 electrons. So there's 30 electrons to place for zinc. 30 electrons. And so we'll place them like this. So that's 10 so far. 12. We can keep going. So we're almost there. If you're unsure where you need to stop at, you can just take a look. I mean, you can count the electrons, but zinc is over here. So we know we're at the 4s, and then we just need 3d10 now. So we're at the 4s, and then 3d10. So let's go ahead and fill those out. Whoops, that's the wrong one. Let's scroll down a little bit more, because otherwise we're drawing into our sulfide diagram there. Like this, like this, like that. So this here would be the regular zinc. This is regular zinc. Now, to make the zinc ion, we need to remove from the outermost shells. So the outermost shell or energy level is our 4s. I know 3d is higher in energy, but we're really looking at removing the electrons from the outer shell first. Those are the most accessible. So we're going to remove from there. And that's essentially all we need to do. Sometimes you can remove from the D if you need to, but we don't need to in this case because it's already full. So we're just going to remove the 2 electrons from the outermost shell, and that should give us our ion. If there were others in the P's, for example, I would remove those first, but 4s is our highest level right now. So we're going to remove those 2 electrons, and that will make our charged zinc ion. So I'm just going to remove these, and I'm going to make it known here that once those are removed, that is zinc plus 2. That's because we removed the 2 electrons from the 4s sublevel orbital. And now we have zinc 2+. So let's go ahead and try that out for the electron configuration. So the electron configuration over here is zinc. We're going to do the neutral atom first. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. And then to make the zinc +2, we want to remove from here. So we're basically just going to remove that 4s2 there. And we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And what you'll probably notice is that we didn't write 4s0. We don't do that. When we have 4s2 removed, we just don't write it in at all. So that's our zinc +2. Now we can go and write out our shorthand notation as well. So for zinc, the shorthand notation, it looks like the noble gas that came before it was, so here's zinc, argon. Argon came before it, and it looks like it ends at 3p6. So argon's basically all the way over here. Here's argon. I'll replace all that underlined stuff by AR, and I'll put 4s2, 3d10. And for zinc 2+, I'll still write argon, but notice I took out the 4s2, so it's just 3d10. And that would be for zinc 2+, it's shorthand notation. And what I want you to notice here is that the valence electrons for zinc are really the S and the D. And so we remove the S, though, because it's the highest energy level. And we don't really need to remove the D. And we'll learn later on that when you have a full sublevel, that's pretty stable. So it would take a lot of energy to go and further and remove more electrons. Every time you move electrons, it requires energy. So there's a limit to how many electrons you can remove. Since the 3d10 is so stable, we're probably not going to want to remove any more. There's some exceptions and everything to that, and we'll learn more about that in more detail, but that's why we stop at the 4s2. It requires more and more electrons because now the remaining electrons are held even tighter to the nucleus that remained there before, or to the nucleus that's there. But generally speaking, when you are in the D or in the D block elements, so in this region, let's say over here, let's go up here in the D block elements, your valence electrons typically are going to be your highest S and your highest D. So your highest S and highest D are going to be your valence electrons, and generally you'd start by removing from your S. And then if you can, sometimes you go to your D. Whereas in this situation over here, where you're in your P block elements, you would remove from the P first. And then sometimes you could remove from the S after. Or if you're adding, you would add to the P. Because don't forget, in the P blocks, you do have some metals that will lose electrons. For example, aluminum. And you have some nonmetals that will gain. So if you're a nonmetal that's gaining, you're adding to the P sublevels. And I believe I misspoke before. If you're a non-metal that's losing, you're removing from the P as well. So if you're aluminum, for example, you'll be removing from P first and then from S after. So if you are a non-metal that's gaining, you're adding to the P. If you are a metal that's losing, you're removing from the P first, and then in some cases you might then remove from the S. Whereas if you're in the D block, your metals, you're not really adding electrons, you're losing electrons, you're gonna remove from S. If there were some outer P's there, you would then remove from them instead, but you're removing from S generally. And then sometimes you can also proceed to remove from D after, if you want to. And that depends on whether there's enough energy available and whether those ions can form more than one charge. So let's go and try a few other practice problems to make sure we understand the concepts of ions forming. We'll do the phosphide example with the ion of P3 minus, and then we'll do the lead ions of P2 plus and Pb4 plus. So before you try those, I recommend you just review this video by going over what cations and anions are, by briefly touching up on what wants to form a cation, which are usually the metals they want to lose, and what wants to form an anion, which are usually the nonmetals they want to gain to become like the noble gas that comes after them. When nonmetals gain their electrons to fill their highest energy sublevel, they look like the noble gas that comes after them. And so we say they're isoelectronic to each other. We say they have the same electron configuration. We did the examples with sulfide there. Cations, on the other hand, are again typically metals that want to lose. They'll lose from the outermost energy shell first. So generally, you'd start by removing from P, then S, then D, depending on what's available. And again, there's a certain limit to how many you can remove because it takes energy to remove electrons. So we did the example with zinc over here, and you have some practice with different types of elements over here afterwards. So review the video first, and then in the next video, you can check your answers for phosphide and the lead ions.